So thank you for thank you for coming to the talk. Thank you for letting me give the talk. So today I want to tell you about statistical models, maximum likelihood estimation, and dual varieties. And the main result will be connecting maximum likelihood estimation with conormal varieties. All of these things are part of bigger subjects, so I'll focus on a specific context, and that's where the result will lie in, is a specific context. So how we're going to start is by playing a game. And so what we're going to have are three people. We'll say one person from Korea, one person from Germany, and one person from Canada, just for the game. And what I'm going to have is 3 Korean coins, right? And they're going to be 2 small Korean coins. And these are going to be weighted the same way. So there's some probability observing side 1 and some probability observing side 2. And then there's a big Korean coin that has a different weight with, again, some probability observing side 1 and some probability observing side 2. And now I'm going to distribute these coins to the people from the countries, and I'm going to give the big Korean coin to the person from Korea, and then the 2 small Korean coins to the 2 other people. So there you go. All right. And then likewise, I'm going to have 3, German coins, otherwise known as euros. And I'm going to have 2 small German coins weighted the same, and a big German coin weighted differently, and distribute them in the following way. Give the big German coin to the person from Germany, and 2 small German coins to 2 other people. All right. And lastly, just so to be clear, I have 3 Canadian coins, and the big one is weighted differently from the 2 small ones, and I give the big Canadian coin to the person from Canada, and then the 2 small Canadian coins to the 2 other people. All right. So
wait, Jimmy, this is the probability of heads.
That's right. Or depending on the country. Yeah. So in summary, each person has 1 big coin from their home country and 2 small coins from other countries. All right. So everybody has 3 coins. So now what we're going to do is generate some data. And so what I'm going to have is a spinner, which I'm going to create right away. And so spinner. And what this spinner is going to do is going to choose a person from Korea, Germany, or Canada. And what I'm going to do after the spinner chooses the person, I'm going to call them. And you don't get to know who I call. I just get to know who I call. And the only thing you get to know is how the coins landed. So for example, I would do the spinner, I make my phone call, and I report back to you 1, 1, 2. And that means the Korean coin landed on side 1, the German coin landed on side 1, and the Canadian coin landed on side 2. So there's a natural ordering. All right, so just again, I spin, I make my phone call, and I report maybe back to you 1, 1, 1. So in this case, we would record the 1, 1, 1 here, and that means the sides of the coin were Korean side 1, German side 1, Canadian side 1. Right? So we record the 1 instance here, and since we observed 1, 1, 1, 2, then we would also record a 1 here. Does that make sense? So we've generated a data set of size 2, and friends love me enough that we're going to do this 1,000 times, and we would collect the 2 by 2 by 2 array of data, which is now conveniently here. Okay, so this is the array of data that we've generated with these coins and with this spinner. So, any questions about the game?
Sorry.
Yes.
So there's 4 columns.
Yeah. Why?
It's flat.
It's flattened. It's
the board is
2, 4, 8.
It's a limitation for the medium.
Yeah, I mean, should this be like...
Let me say, so here I'll say U112 is the number of times we observed 112. So 18 times we observed Korean on side 1, German on side 1, Canadian on side 2. U22 in this case is 194, so we observed the Korean coin on side 2, the German coin on side 2, the Canadian coin on side 2, 194 times.
My question is there any particular geometry to the...
No, I just flattened it.
Because you didn't have a 3-dimensional blackboard.
This is the second. All right. So now what we'll be interested in is what's the probability of actually observing, let's say, like the occurrence of 1, 1, 2. And so this is a little bit messy, but we described the game so you don't have to look at this in detail. But the thing that you should take away is that on the right-hand side, we have some unknowns, or some statistical parameters, which are pi, alpha, beta, gamma, and so on. And these are going to be the weights of the spinner and the coins. So if you knew these unknowns, you can plug them into here and determine the probability of actually observing 1, 1, 2, right? But you don't get to know these weights. So instead, what we're going to do is just work with these with these p coordinates. And so if you eliminate these unknowns on the right-hand side, what you get is the following. You get actually a polynomial relation amongst the p's. And the miracle is that it's actually a nice polynomial. And it's in fact the hyperdeterminant of 2 by 2 by 2 tensors of this form. Right? So our algebraic statistical model in this context will be the solution set of this polynomial. So this solution set lives in some seven-dimensional projective space.
So Jose,
yes?
So the context is the size of the coin. When you talk about context specific, you refer to the size of the small coins and big coins.
Okay, yes. I'm not sure on how to relate it exactly into the definitions of context-specific model. I was using the word context as in like broader general context.
Where does it come in that you only have 2 different types of coins rather than 3 types of coins?
Let's look at the parameter.
That's in the parameterization here. That's just how I've said we're going to play with this model, and that's how the parameterization is defined. Just one example. Let's see, what else? Oh, yeah.
So getting the hyperdeterminant is dependent upon that, or?
On the parameterization, very much, yeah. I mean, if you choose a different type of parameterization, then you're going to get some different variety. So.
If you're not in degrees of freedom, you might get everything.
Yeah, exactly.
Yeah, with fixing the degrees of freedom so that you expect a hypersurface.
I'm not sure what your question is.
I'm not sure either.
Okay, well, so I think we'll continue on then. So let's stick with we have a solution set of this polynomial equation, and that's going to be x. And now what we're going to do is introduce another coordinate, which we're going to call ps. And with this new coordinate, we're going to introduce a new variety called xh, which now lives in P8. So we went from P7 to P8 by introducing another coordinate. And this variety here is going to be the solution set of our original hyperdeterminant, as well as this linear relation here dependent on h. Now in this talk, we're going to keep things simple and just take h to be 1, 1, 1, 1, 1, 1, 1, minus 1. And the resulting linear relation is very easy. It just says ps is equal to the sum of the coordinates. So what you should think of is that ps is keeping track of the sum of the coordinates, which is what you want to do in statistics, is have ps equal to 1 at the end of the day. Right? So our variety xh is this linear relation as well as this polynomial here. Right? And the goal is by understanding this xh, we'll understand x, and then we can say something about p's in relation to our data here. Okay? All right, so now what do I mean by which p do we want to get to actually describe the data? I've been saying maybe best p, but what do I mean by best p? Well, what we have is what's called the likelihood function of our data. So the likelihood of actually observing some particular data of, like say, size 1,000 will be taking the probability that of actually observing the event, raising it to the number of times we observe the event, and multiplying everything out together, scaled by a multinomial coefficient. Right? So this is the likelihood of observing this data. You would take these numbers here and plug them into here. U plus in this case will be 1,000, which is the sum of all the entries. Now, this would be the original likelihood function, and what we're going to do is make it nicer and homogenize it so we have a degree 0 Laurent monomial So we put PS to the minus U plus plus plus. So all the exponents sum to 0. Right? So this likelihood function is going to be on xh, and we want to find p hat, the point that maximizes it on the set that we're interested in. And this point has a name, and it's called the maximum likelihood estimate in the nicest cases. So I've omitted some details on when this, well, I'll keep on going, and then if there are questions about details, I'll answer them at the end. Okay, but any questions so far? So just to review, we have this function, we have this variety, and now we want to find the best point, optimize this function on this variety. And to do that, we're going to find critical points. Just thinking back to calculus, how do we optimize a function? We find critical points. And what we're going to do is find all complex critical points. And then once we found the complex ones, we'll restrict to our case of looking at the real ones, and then look at the real ones with positive coordinates, and then pick our favorite one, the one that gives us the biggest likelihood. So how we do this is we solve what are called likelihood equations, which I'll tell you about on the next slide. Some advantages of numerical algebraic geometry that we saw in the last talk is we can use a homotopy. So for some particular set of data, we'll have some set of critical points. And then we can use a homotopy to generate this set of data to a different set of data and a different set of critical points. Right? And this process hopefully can be done very quickly, and we can get solutions to various choices of data very, very quickly. Right? So that's one motivation to find all complex critical points. Excuse me. So what I want to present to you now is a classical geometric formation of the likelihood equations. That's in Serkan and Barron's paper. Well, yeah. Anyway, it's a slight adjustment of that formulation with this PS. And what we're going to have is suppose XH has codimension C, and defined by the vanishing of these Fs. Right? So in the previous example, we had just 2 Fs, and now I'm saying, well, whatever we want here for different Fs. And now, ready for our first miracle on this, or second miracle if you thought the hyperdeterminant was a miracle, was that the gradient of the likelihood function turns out to be a rational function after you scale it appropriately. And so earlier we had the u's and the exponents, but when we look at derivatives, the u's end up coming down and we divide by the p's. So after we clear denominators, the result will be a polynomial function in the p's and the u's, whereas before we might have expected to have the u's and the exponents, and that would have made things very difficult. Okay, so p and xh, so a regular point here, is going to be a critical point if and only if the gradient of our objective function is orthogonal to the tangent space, right? Or equivalently, this is saying that the gradient of our likelihood function is in the row space of the Jacobian. What's the Jacobian? Well, it's a matrix of partial derivatives of the f's. So here we have f's that define our xh. And then here's this matrix. So it's a k by n plus 2 matrix. And it's just given here. So we want to know when this vector is in the row space of this Jacobian. So this is a geometric formulation. Any questions about the geometry? Okay. So then what we're able to do is actually get equations now. I'll present to you an overdetermined system. And so we stick the gradients of the likelihood function on the top row. And then what we do is we take the f's, we take the numerators of the c plus 1 minors of this matrix here, and then now we have a bunch of equations. And we would hope that this would be everything, but now we have to saturate by the singular locus of xh. And then we also have to saturate by this product of unknowns here. So we have to saturate by the singular locus, well, just because we want to stay away from the singular locus. And we saturate by the product of the unknowns, so the likelihood function is non-zero. Okay, or we can think of also as things going to infinity. Remark is, in this paper here, we gave an alternate square formulation that allows us to do some new computations for some other statistical models. But this is just an overdetermined formulation I presented here. Okay. So what's next is we're going to come back to our original example and do 3 different experiments. And so here's our data. Say we had this data set here. So say I went to give this talk in China, and we made a bunch of phone calls and we collected this data. Maybe we went to then Japan and then collected this data here, and maybe we did today, we collected this data here. All right. Well, we can then find the number of critical points of the likelihood function for each of these sets of data. And what we find in each case is that there are 13 complex critical points. The number of real critical points can change. So there can be 3 real critical points in this set of data. There can be 9 here, 5 here. But there's always, for general choices of U, there are always 13 complex critical points. So this number has a name, and it's called the maximum likelihood degree of XH. All right, so this is going to be the numbers that I'm interested in computing are these maximum likelihood degrees. So given a variety, XH, or given this type of variety, XH, we can then ask, what's its ML degree? Right. Okay. Yes?
Is it clear why it's always the same number of complex critical points?
That's from just genericity, like for general, because just a genericity argument.
Equations of the same shape but different parameters. So that's
Oh, but it's not always the same. Sorry, it's like for special choices of data, like the number of critical points can drop. So now we're to the third thing, and that's dual varieties. And so what we're going to consider is, again, XH with the same assumptions as before. And what I want to tell you now is what a conormal variety is. And the conormal variety lives in a product of 2 projective spaces. The first projective space will be the p-coordinates, which we've been messing with this entire talk. And the second projective space will be in b-coordinates, which are now new on this slide. And so how do we get a point in this conormal variety is the following way. We take p in XH, and then or regular point P in XH, and then we take a normal vector. And then we take this normal vector to the tangent space of P and call it B. So we now have a point PB inside the conormal variety. We do this over all the regular points and all possible choices of normal vectors, and then we get the conormal variety. All right. The dual variety of XH is just the projection of the conormal variety to the b coordinates. And if you projected the conormal variety to the p coordinates, you would have recovered the original variety. Now, if you didn't like that definition, I can give you a constructive one. And the defining equations of this conormal variety are given by f's, the c+1 minors of this extended like Jacobian, or this extended Jacobian by b's, and then you saturate by the singular locus of xh. So that's another definition of conormal variety, and hopefully one of those 2 will make you happy. Well, I guess, are there any questions about what we've talked about so far? Happy? Okay, so now we're ready for the result, and which connects these 2 maximum likelihood estimation and conormal varieties. And it says, well, let's fix an algebraic statistical model XH, and we're going to suppose PB lives inside our conormal variety. And for general U, this relation holds. If and only if P is a critical point of the likelihood function on XH. So we have this conormal variety, and we have this relation that says take the coordinate-wise product of the point PB. So you have a P and a B, take their coordinate-wise product, and you should get something that's expressed only in U's. And this occurs if and only if P is actually a critical point of the likelihood function. And the important takeaway is that the ML degree of xh actually equals the number of solutions of this relation on the conormal variety. So by solving this equation on the conormal variety, we can recover the number of critical points. All right. So now now I want to give a bijection between critical points. And so consider this likelihood function now in the b coordinates, now on the dual variety xh. And now we can reformulate the previous theorem by switching the roles of p's and b's, just by projective duality. And so we have that the relation we saw in the previous slide holds if and only if b is a critical point of the likelihood function of b on the dual variety. Right, so we flip the problem around. Now, as a corollary to that, then that's saying that there's a bijection between the critical points of the likelihood function on xh with the critical points of the likelihood function on xh dual. And it's given by this relation that we've now seen a third time. Right? So that's the idea. Now, in this last minute, I'll tell you how we can use the bijection. And it's in the following way. So for our first example, xh is defined by binomial-like quadrics of this form here. And what we can do is solve dual likelihood equations, meaning we can solve critical points of the likelihood function in the b coordinates on the dual variety, and we again find 13 complex critical points. And then if b is one of these critical points, then we can recover a critical point on the primal to our original problem by taking the u's and dividing by the b. And then there is our critical point to the original problem. Okay. So that's one way you can use a bijection, is by working on the dual and then bringing things back. And then in the final, I guess, 30 seconds or so, I'll say that when x is the hyperdeterminant of 2 by 2 by 2 by 2 by 3 tensors, we found the ML degree is 71 using a different formulation. But again, the dual variety is defined by binomial-like quadrics, where these quadrics are 2 by 2 minors of various flattenings. The hyperdeterminant of 2 by 2 by 2 by 2 tensors has almost 3 million terms, and but the dual variety is still defined by 2 by 2 minors of the flattenings. So hopefully you could make an approach using this. You can approach the problem using this dual formulation. And so I'm out of time, so I'll leave things there. And here are some references.
Your critical points, were they several local minima?
In the one, I didn't check it for these examples, but we did some, for different models, we saw that they can have several local minima or maxima, whatever.
Jan?
2 questions. Does this work when the dual variety is not a hypersurface?
Yes.
And then what was this determinant and permanent?
So this was a bonus slide that I didn't have time to say, but
Flash long enough for Jam to see.
so a variety walks in the door. First thing you ask, what's its dimension, right? The second thing you ask, what's its degree? And if a permanent determinant walk in the door, then those answers are the same. But then if you ask what is its ML degree, which hopefully you will after this talk, you see that the determinant of 2 by 2 matrices is 1, has ML degree 1, but the permanent has ML degree 2. In the case of 3 by 3 matrices, the ML degree determinant of 3 by 3 matrices is 10, where the permanent is 36. And these are just some computations. I don't know what that means in broad context of things, but they thought they were kind of cool that they're different.
So how does this ML degree compare with the degree of the dual variety?
So you can look at its. What you can do is you can look at the multi-degree of the conormal variety, and it should be one of these entries of the multi-degree of the conormal variety.
And I'm a little confused also because over complex numbers, the determinant and permanent are the same when n equals 2.
So there I was also going to have a second slide that has a second a second table, and instead of, I talked about this h, and it had these 1s and -1s, but you could have changed the h to be general. And if you change the h's to be in general, this 1 now becomes a 2, and this 2 remains a 2. And they're the same there, and then they're different for the next ones.
Any other questions?